Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And yesterday I did a bonus video about a professor, very famous professor in our field, Dr. Walter Saucier, who I knew back in the 80s, and I used to see him at the local chapter of the American Meteorological Society meetings. And he would challenge me back in those days. I was very, very young in the business, obviously. And he came up to me one day and said, "So on what kind of day do you think snow melts quicker? A sunny 50-degree day or a rainy 34-degree day?" Well, my gut reaction told me that it would be the sunny 50-degree day. And again, he pointed out to me that I was dead wrong. And so we're going to talk about the reasons why that is the case and also some additional factors that contribute to snow melt. Of course, in central North Carolina, first you have to have snow to melt, which is the first obstacle that we have to come across. But anyway, that's another matter. All right, so let's go on ahead and delve into this here. So, what conditions melt snow the fastest? So let's say we have a sunny day. Now the sun is not going to be that high in the sky during the winter. This is just for artistic purposes. And the white rectangle there at the bottom is the snowpack, and so the sun is beating down on it and trying to get rid of the snow. Well, freshly fallen snow has what we call a high albedo. Albedo is a scientific term for reflectivity. In fact, freshly fallen snow reflects about 95% of the incoming solar radiation. So as a result, blazing sunshine really has very little effect on a fresh snowpack, okay? Now, if the snow melts and then evaporates, heat is taken from the air. We've talked about evaporational cooling before, where if rain falls into dry air, then the evaporation of that rain into that dry air causes the air to cool. And there's sometimes when it may be raining initially, and then if enough evaporational cooling takes place, the rain can actually turn over to snow. So evaporation is a cooling process. You know this when you get out of a swimming pool or get out of the shower. As the water evaporates off of your skin, you feel cold. So that's an example of that, or a couple of examples. If the snow sublimates, which means it goes straight from solid to vapor, heat is also taken from the air in that kind of a situation. So all of these processes are competing against the snow melting, or at least the snow melting at a fairly rapid clip. Now, let's take another scenario here where it's raining. And I'm going to say, just for this example, the temperature is 40 and it's raining and the air is saturated. So the temperature of the air is 40, the dew point of the air is 40. The temperature of the snowpack, obviously, is less than or equal to 32, okay? So the temperature at the top of the snowpack is 8 degrees cooler than the dew point of the air just above it. So what's going to happen in that situation? You're going to get condensation, okay? And condensation releases heat. It's the opposite of evaporation in that sense, okay? Evaporation is a cooling process. Condensation actually releases heat into the air, and that heat then helps to melt the snowpack more effectively and more rapidly, okay? So the rainy 34, 35, 40-degree day is going to melt snow a whole lot quicker than a sunny 50-degree day. Okay, now there are some other factors that come into play which you may or may not have thought of. Number one, as the snowpack ages, it becomes darker and dirtier, and the albedo lessens. The albedo is pretty much proportional to the degree of whiteness of whatever surface you're using or looking at. And so as the snowpack darkens, the reflectivity lessens, the absorption increases, and it starts to melt faster as a result of that. Now, snow is a great absorber of infrared radiation, okay? And that's the type of radiation that clouds, perhaps, up in the sky, are emitting toward the ground, okay? So if the cloud temperature, let's say that we're getting into one of those situations where it snowed a day or two ago, and it's starting to warm up aloft, but it's still, pretty cold near the ground. So if the cloud temperature is above freezing, let's say we have a cloud at maybe, 1,000, 2,000 feet, and that cloud temperature is above freezing, then it radiates that heat toward the ground, and the snow can melt even if the air temperature just above the snowpack is below freezing, okay? So when it starts to warm up aloft, that can be a problem as well if you don't want the snow to melt. Number 3, dark road surfaces, and here we get back to the albedo thing, absorb most of the incoming solar radiation. This is one thing that used to really make me mad as a kid, is that after it snowed, I'd hear the forecast for the next day, sunny and cold with a high of 28. And I'd think to myself, well, 28's below freezing, so I'm going to be able to go sledding all day tomorrow. Wrong. All of a sudden, by noon, the water was streaming down the hillway, okay? And as a result of, or what happened there is the fact that the road surface was dark. Maybe there was one little spot where it melted all the way through, and then that heated up, and then it started to gradually spread out, okay? And even though the air temperature was below freezing, the snow was melting like mad on top of that road surface, and the sledding was pretty much over at that point. And then finally, warm soil can melt the snow from below. So supposing you had a 2-week warm spell, okay? And then all of a sudden it suddenly got cold and it snowed and you got 4 inches. Well, the soil temperature, especially as you go down a few inches, is still going to be very, very warm. And as soon as that snow stops falling and accumulating, then that warmth is going to penetrate up from the ground and it's going to start to melt the snow from the bottom up. And so that can play a major role as well. I remember there was, let's see, I'm trying to remember here. There was this one situation where we had the gridlock. I can't remember if it was 2005 or 2006, but we had been unusually cold for 2 or 3 days. Like we had been below freezing almost constantly for 2 or 3 days. And you remember, for those of you that were here, we had that light powdery snow. It was just almost like dust. But everybody got really, really worried about lunchtime that is this the beginning of something big? And so they all got out on the road, and the interaction with the tires and this dusty snow, it melted the snow, and then because the ground was so cold, it immediately refroze that melted snow and turned it into a sheet of ice, okay? That is a condition or a set of conditions that almost never happens in central North Carolina because we just don't have that many times where it's below freezing day and night for 2 or 3 days in a row. But we had it in that particular case. So it was the combination of human activity and an unusually long and intense cold spell prior to that that transformed this innocent powdery snow into a skating rink. And of course, it wreaked havoc with people getting home that day and getting out of school and all of that type of thing. If you were here that particular day, I'm sure you remember it, and we'll probably never see anything like it again in our lifetime. So those are all, or at least some of the conditions, a lot of the conditions that lead to the melting of snow. And so we have a lot going against us here in central North Carolina with our latitude and so forth. But every once in a while we pull it off, and for snow lovers, there's always hope. All right, folks, that is it for now. That is the bonus weather video for this Wednesday. The next one will be coming up Friday, and the next daily weather update, of course, coming up tomorrow. So you all have a great Wednesday evening, and we'll talk to you again, late tomorrow afternoon. See you later, everybody.